All right, team, we're actually going to combine sections 8.3 and 8.4, polar coordinates and graphs. These are kind of an introduction to what polar coordinates are. So we're used to working with what we call the rectangular coordinate system. And that would be this picture below. Rectangular coordinate system where we have the x-axis, the y-axis, and typically it's on a grid of squares or rectangles where you can move over 2 and up 3. And on the rectangular coordinate system, we use ordered pairs in terms of the x-coordinate, the input, and the y-coordinate as the output. Well, we have something called the polar coordinate system. And this is based on a point that we call the pole. Okay, so that would be the origin, 0, 0. An array, which we call the polar axis. And that is basically the positive side of the x-axis. This is what a polar coordinate system would look like, where our pole is right there at 0, 0. And all of our angles that we're going to be talking about is based right here with the positive x-axis. Just like when we were studying angles before in standard position, all of those angles are in reference to that x-axis. So any point, even in the rectangular coordinate system x, y, can be located by giving what we call the directed angle. That would be theta, and the directed distance, and we'll call that r, like our radius. And I'll explain why they're using the terms directed here in a minute. And we have an ordered pair for that polar coordinate system where r is our output value and theta is our input value. So we have to be careful of the order. It's still r theta. So in the rectangular coordinate system, just like we would give the value of the x and y, the x coordinate to the right or left, y coordinate goes up or down, instead we can give it in polar coordinates where r would be the length, let's say, of the hypotenuse of that triangle, and theta would be the angle between that positive x-axis in standard position and that terminal side of that angle. So in polar coordinates though, instead of using those little rectangles, we use circles because it's easier to determine what the radius is. In other words, that distance out. So for example, this would be a radius of 1, 2, 3, 4. So we can just go along the circle of that angle and count what's the distance from that theta. Now you may notice here that we have a theta with a positive r, and that gives us the point towards that terminal side of that angle within that direction. Well, if we were to find that angle but move away from it in the opposite direction, we would use a negative r. So I know we think of radius or hypotenuse as always being a positive number, but that's why we're giving this r the title directed distance. We don't have a negative distance, so instead the negative means direction. Are we moving towards the terminal side of that angle, or are we moving away from the terminal side of that angle? So basically it's like a reflection where you're flipping sides. But instead of over the x-axis or y-axis, you're flipping it just directly over the pole. That's where this comes in. That's that explanation down there below. So let's remember some of our formulas from before to help us convert the polar coordinates into rectangular coordinates and vice versa. If we remember the definition for the cosine of theta, we can take the x value and divide it by the r value. Well, if we solve for the x, that means our x coordinate equals that directed distance times the cosine of theta. So there's a formula that we can use. Same thing for sine theta. It was defined as y over r. So if we multiply both sides by r, then that tells us that the y coordinate is equal to r times the sine of theta. Another formula is basically the Pythagorean theorem, where we consider x squared plus y squared equals r squared. So if we know an x and y, we can find r. And tangent theta, remember, is always your sine over your cosine, or y over our x. And again, as long as the x isn't 0. So let's do a couple of examples of coordinates. So here's example A. It's given it to us as polar coordinates. We can tell because that second coordinate there, they're giving it to us in degrees. And so we have a directed distance of 4. It's positive, so we're going to move towards the 135 degrees. And this is our theta. Well, remember, 135 degrees is roughly right here, because that's about the same, or it is the same, as 3 pi over 4. So we're going to move towards that angle, but at a distance of 4 units. So here we have 1, 2, 3, 4. So there is our coordinate for an 135 degrees. So there's that coordinate point in polar coordinates. In part B, again, we have a directed distance of -3 and a theta of pi over 6. Well, pi over 6 is right here. So if we were to go 3 units, we would be going towards that pi over 6. But since it's -3, we're actually going to go over here in the opposite direction, and then 3 units away from pi over 6. So there's 1, 2, 3 units away from pi over 6. So that guy would be a -3 pi over 6. So for problem C, we still have a positive r. That means we're going to be moving towards the angle given. It's just now the angle is negative this time. So a negative pi over 2 is down here, negative pi over 2. It's like a negative 90 degrees, but we're moving towards that negative 90 degrees, 2 units. So 1, 2. So there's the coordinate 2, negative pi over 2. Now, one thing to note is if we're given a point in the rectangular coordinate system, in other words, x, y, it will always plot one unique point. Every point has a unique rectangular coordinate. But that same point can have infinite number of pairs of polar coordinates. In other words, we can use positive and negative angles. We can use positive and negative directed distances. We can also go around it 3 or 4, 1,000 times if we wanted to, however many revolutions. So just like the sinusoidal functions, where it has a period and it keeps repeating over and over and over again, there's a lot of different ways to get these points as well. Typically, we want to keep those points as easy as possible, but if we're needing to find more than one point, we always can. So let's do an example of that. In example 2, we're to find 4 different pairs of polar coordinates for the same point that has the rectangular coordinates. Okay, if it says rectangular coordinates, that's our hint that we are given x and y, and as described below. In other words, they're wanting us to come up with a positive directed distance, that positive r, but a negative angle, negative r and a positive angle, positive r, positive angle, negative r, negative angle. And it doesn't matter which one we find first, but we need to at least find one, an r and a theta. Well, remember, we have a couple of formulas. X squared plus y squared equals r squared. So we can plug in our x and our y. 6 squared plus a -6 square root of 3 squared should equal r squared. So we get 144 equals r squared. So r is going to equal 12. Now, it could be a positive 12, it could be a negative 12. Well, right off the bat, then we can plug in, you know, positive 12 here. This one asked for a negative R. This one asked for positive R. This one asked for a negative R. So right off the bat, we can plug in the R values. So we have half of all those points that we're looking for. But now we have to find different angles that fit. So if we were to graph the 6, -6 square root of 3, and we have a y of -6 square root of 3, we have an x of 6. So, you know, we would have a point somewhere down here in quadrant 4. So what we're wanting to do is find what those angles are. So let's remember cosine of theta equals x over r. So in this case, we would have 6 over 12. So we have a cosine value of 1/2. So when does cosine equal 1/2? Positive is in the first and the fourth quadrants. So if we're looking at the fourth quadrant, there's a couple of angles there that would work. The reference angle would be up here at 60 degrees or pi over 3, which means this angle here is a negative pi over 3 or positive 5 pi over 3. So we have two choices if we're going down in that direction towards that angle. If we use the positive r, we can have a positive angle of 5 pi over 3, which would be this guy, positive r, positive theta. Or we can go towards that angle using the negative degree, which is negative pi over 3, which would be that angle. Let's now look at the negative r value. That means if we use the negative r value, we're going to be going in this direction. Again, still the same reference angle. So if we were looking at pi over 3 in the first quadrant, then this would be a 2 pi over 3 in the second quadrant. Or if we're looking at the negative angle, that would be a negative 4 pi over 3. So for negative 12 with a positive angle, we can use 2 pi over 3, or negative r, negative angle, negative 4 pi over 3. So again, we can have positive r's towards the angle in that original position, or we can use a negative r where we're going toward in the opposite direction and then flip it. So if the angle's in quadrant 2, the negative r would put us in quadrant 4. So just as a reminder, a positive r goes toward theta, a negative r goes away from theta. So let's take a look at example 3. We want to change each rectangular equation, and again, when they say rectangular now, we know that it's in terms of x and y, and we want to give the equivalent polar equation, which means we are dealing with r and theta. When we're doing it in a polar equation, we want to put it in terms of r equals. Usually with rectangle, we have a y equals. Generally with polar equation, we want it in terms of r equals. So we need to substitute in for every y and every x. In part A here, y is equivalent to r times sine of theta. X is equivalent to r cosine theta. So we just plugged in from page 1 those little substitutions. And now let's get r by itself. So we get r sine of theta minus 2r cosine theta equals a negative 4. We can factor out the r, and we get r equals a negative 4 divided by sine theta minus 2 cosine theta. For the second one, we have the equation of a circle, x squared plus y squared equals 25. But remember, x squared plus y squared equals r squared. So we get r squared equals 25. We take the square root, we get r equals plus or minus 5. But really, that's two equations, r equals 5 and r equals negative 5. These are the same graph. Let's actually graph B. So if we think of terms of a polar equation, we've got our radius can be +5 or -5. So let's just say +5. And our theta can be anything. Our theta can be pi/6, it could be pi/3, it could be pi/2. So if we look at all of these possibilities, 1, 2, 3, 4, 5 units away, we can have it here, 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 here. So again, our theta can be anything. So if we were to combine all radiuses of 5 or distances of 5, we would get a circle of a radius 5, which is the same equation as the x² + y² = 25. So even if you had the -r, you take any of those angles, you go in the opposite direction, you're still going to land on that unit 5 circle. For example 4, now we have an equation in polar coordinates, so a polar equation, and we want to write a rectangular equation, which means we want everything in terms of x and y, not r and theta. Well, the tough thing here is we have an r and we have the 1 minus cosine theta. So one of the things that we can do is cross multiply and see if we can do some substitutions. So we can get r times 1 minus cosine theta equals 1. When we distribute, we get r minus r cosine theta equals 1. Remember, r cosine theta is x. Then we can add x to both sides. We get r equals 1 plus x. But r by itself, we can't really substitute in for, but we can do it if it's squared. So let's go ahead and square both sides. So r², we can substitute in x² + y². The right-hand side, if we were to distribute, we would get x² + 2x + 1. So we get y² equals 2x + 1. So you get y equals plus or minus the square root of 2x + 1. Now, a couple of notes I want to make. Once we're here, we have a rectangular equation. Everything is in terms of x and y. It just may not be simplified. If we want to graph, go ahead and solve for y. That way we just put it straight into our calculator. In example 5, we're asked to graph each polar equation by plotting points. This can be a little bit tricky because remember, we can have one point with several different values, different r's and thetas that can get us to that exact same point. So let's start by just plotting those quadrantal points. So let's choose some of the angles that we know: 0, pi/2, pi, 3 pi/2. And let's see what those look like. When our theta is 0, we end up getting 1 for our radius. At pi/2, we get 0 for our r. Plug in pi, we get 1 for our radius again. Plug in 3 pi/2, we get 2. So let's plot those points. At angle theta of 0, we get a radius of 1. So this might be a little small. At 0, we have a radius of 1. At pi/2, which is up here, we have an r of 0. At pi, we're back here at 1. And at 3 pi/2, we're down here at 2. So it doesn't quite tell us what this equation is going to look like. So let's figure out some more points that might help us. Remember, this is pi/6 here. So let's start with that. If we're at pi/6, and remember, we're dealing with sine, so the value at pi/6 is going to be the same as the value of 5 pi/6, because those sine values, the y values in quadrant 1 and quadrant 2 are the same. So we can go ahead and put those two together. If we plug in pi/6, we get a 1/2, and so 1 minus 1/2 is a 1/2. If we were to do negative pi/6, which would be the same as negative 5 pi/6, we would get a negative 1/2. So this would give us 1.5. So let's go ahead and plot those again down here: negative pi/6, negative 5 pi/6, or you could put in the positive values too. That's fine. You could put in 11 pi/6 or 7 pi/6. pi over 6, we were here at a half. 5 pi over 6 here at a half. Negative pi over 6, 1.5. Negative 5 pi over 6, 1.5. Our shape looks like this. Almost like a heart that's not supposed to come down to a point. It's curvy because again, it's based on a sinusoidal function. So that's what that guy looks like. Just a rough sketch. Now let's focus on B. R equals 4 cosine of 3 theta. So again, let's plug in an R and a theta. Let's start with the nice angles that we know. 0, pi over 2, pi, 3 pi over 2. Cosine at 0 is 1. So even if it's 3 times 0, it's still 0. So that's going to give us an R of 4. If we plug in pi over 2, that means we'd be taking the cosine of 3 pi over 2, so that would be a 0. Pi would give us 3 pi, so we'd end up with negative 4. And 3 pi over 2 again would give us a 0 again. So if we were to plot those 4 points at angle 0, we would be at 4. 1, 2, 3, 4. At pi over 2, we would be at 0. At pi, we would be at negative 4. So remember at pi, if our R is negative, if we go towards it, we would be here, but then we're told to move away. So we're back here. This is negative 4 pi because we moved away from the pi. So if pi is this way, we're going to go in the opposite direction 4 units. We actually end up at the same point. And then at 3 pi over 2, we're back at 0. Well, that only gives us really 2 points. And so we've got to come up with some others here. Because we're multiplying by 3 up there, we can choose some values that we like, might give us some nicer numbers. I would choose pi over 3, so the 3's would reduce. Remember, since it's cosine, cosine has the same values in quadrant 1 and quadrant 4. So we can do a positive pi over 3 and a negative pi over 3, and it would give us the same value. That would give us a negative 1. Negative 1 times 4 gives us a negative 4. And pi over 6, negative pi over 6, gives us pi over 2, which would be 0. 4 times 0 is 0. Let's see what those technically 4 points would give us. So if we go towards pi over 3, which is up here, this tells us to go to negative 4 directed angles. So instead of going towards pi over 3, 4 units, we're going to go away from pi over 3 down here in quadrant 3, 4 units, 1, 2, 3, 4. And the negative pi over 3 here also is a negative 4. So instead of going towards negative pi over 3, we're going to go this way away from negative pi over 3, 4 units. Then we have pi over 6, which is again 0. And we have the negative pi over 6, which again is 0. So notice we're getting zeros at pi over 6, which means we're not going to cross that pi over 6 when we come up here to the 4. In other words, this little loop isn't going to hit that pi over 6 because we're at 0. If it hit it, we would come up with that point. So if the pi over 6's give us 0, then everywhere that we have these little loops here, they're going to be thin. We know they're not going to go out. And you can always plug in pi over 4 or anything like that, see if it gives you a value that you like, but it's basically going to give us what, in this case, looks more like a fan, like a 3-blade fan. So the very last page is just to kind of give you an idea of what some of these polar curves look like. So those of you that are going into computer science, if you're thinking about doing any sort of media arts and you're wanting to get things to look a certain way or to have certain type of shapes or repetition, you might be using some of these polar curves in your programs. So the circle is just R equals either sine or cosine, depends on which direction the circle's going. The second one is called a cardioid, which is similar to the first one that we did. Then we have a one loop limacon. We have an inner loop limacon. We have a lemniscate, if I can always pronounce these correctly. We have a rose curve. So when the n is even, this is similar to what we had on that last example. If the n is even, an even number of loops, depending on how many ends you have. Or we have a rose curve that has an odd number of petals. I think this is more like the last one that we had. We had 3 theta, right? So rose curves. And then the last one was Archimedes spiral, and it can keep going kind of in that direction there. So these are pretty cool. And we've done, like I said, we did a circle on one of those examples. The only other one that I might show you is if you have something like theta equals pi over 3. So we have here, this is pi over 6, up here, pi over 3. All that we know is that our angle is pi over 3. All that means is our radius can be anything. So for this point, it has to be pi over 3. Our radius could be 2. Our radius could be -4. But the theta still has to be pi over 3. So if my radius is 2, if my radius is -4, if my radius is 0, doesn't matter. It just means that my angle is pi over 3. So if you have something like that, where it's just the theta, you're going to get a line. So I will not require you to have the name and the formulas memorized. This is just an introduction. Know that they exist. Let's actually go back to these 2 equations in example 5 and show how to do them on the calculator. That would be our last thing. So we're used to graphing again in the rectangular coordinate system. So if we go to mode, just like we had, let's see, radians and degrees, we're used to graphing a function. So we're going to go down to where it says function, scroll over to polar, and we want to graph polar equations and hit enter. So now notice if we go to y equals, it actually no longer says y, it says r. So the first equation that we did was 1 minus sine theta. So 1 minus sine, and notice this button here where we normally go to put in our x, it has a t, that's for the parametrics, and theta, we're going to choose theta. And our window, looks like they may have already set it up to standard. Let's zoom in. There we go. So there's the first one that we did. The second one that we graphed, let's clear that one, was 4 cosine of 3 theta. So 4 times the cosine of 3 theta. And let's zoom out a little bit, down to 3. And that's what we get. So it's kind of nice that you can also go to your calculator as long as you have it in terms of R. R equals blank, just like Y equals in order to put it into your calculator. All right, guys, that's it for me. Have a great weekend. Come and see me if you have any questions or need any help or just want to say hi. Talk to you soon. Bye.